Okay. One part of this inequality is very easy to show. Why? Because if you have, there is always a way of disconnecting a graph by deleting some edges. The edges, all the edges incident to one given vertex. So if you pick up one vertex which has as few edges incident to it as possible, meaning with the degree equal to small delta, which is the minimum degree in the graph, of course, you can disconnect the graph just by leaving that vertex by itself and all the others in another component, okay? But it might be that it's not necessarily that you can have even less. And this graph is very nice because it represents exactly the fact that these two inequalities may be strict, okay? Here what do we have as small delta? Okay, let's see, 4, 4, 4, 5, 4, 4, 4, 4, 5. So 4 is a small delta. But we can see that if we delete these three edges, we disconnect. And so 3 is less than, strictly less than 4, which is small delta. So surely kappa prime is greater than or equal to 3. Actually, you can try all other ways of disconnecting and never the deletion of two edges will disconnect the graph. So 3 is actually kappa prime. You need at least the deletion of 3 edges in order to disconnect the graph. But do we need 3 vertices? No, we can have a vertex cut given by these two, or these two vertices, okay? And the deletion of these two, or alternatively of these two, will again disconnect the graph. But it's not enough to delete just one. So kappa is 2, kappa prime is 3, and small delta is 4. And so in this case, for this very nice graph, you have the occurrence of the strict inequalities. Okay. I don't give the proof. Okay. We'll go to another thing which is related to connectivity, which is blocks. Okay. A connected graph which has no cut vertices is called a block. Okay. Every block with at least 3 vertices is two connected. Okay. Because why? Because the existence of cut vertices tells you that you can disconnect by deleting one. And so every block with at least 3 vertices is necessarily two connected. What do we call, this is if I have a whole graph and I call it a block. Now we can talk about the blocks of a given graph. It is a subgraph, which is a block, and again what? Which is maximal with respect to the property of being a block, okay? It is not an equivalence relation, so the blocks are not disjoint from each other as are the components. The components are disjoint from each other, okay? So if you have two components, there is no vertex in common, no edge in common. If you have blocks, you may have vertex in common between different blocks. And for instance, take this graph. This is just one graph with 3 components. Let's see its blocks. We have that this vertex by itself is part of 3 different blocks. This loop, which by itself has no cut vertices. This loop, which by itself has no cut vertices. This edge, which by itself has no cut vertices. Okay, so this vertex is shared by three different blocks of the graph. And here we have a cut vertex, and so cut vertices actually are the ones which identify blocks in the graph, and so this tells us that on one side you'll have a block, on the other side you'll have another block. And here again you can find a cut vertex here, a cut vertex here, and so these cut vertices will be the ones in common with this block and this block, or this block and this block. Okay? Blocks are also rather interesting when examining the connection of a graph. A family of paths in G is said to be internally disjoint if no vertex of G is an internal vertex of more than one path of the family. What is an internal vertex of a path? Not the origin, not the terminus. So you say that two paths are internally disjoint when apart from possibly the ends, the origin and terminus, all other vertices are not in common between the two paths, okay? And the whole family of paths is said to be internally disjoint if no vertex, what is written here? No vertex of G is an internal vertex of more than one path of the family. And we have this theorem: a graph G with at least three vertices is too connected, okay, kappa is greater than or equal to 2, if and only if any two vertices of G are connected by at least two internally disjoint paths. Okay, again, no proof. Corollary: if G is too connected, then any two vertices of G lie on a common cycle, which is rather easy out of this. Okay, but just to understand what is going on in a two-connected graph. Something which we do not use here now, but which will be used quite a long time after in the chapter on planar graphs, is the idea of subdivision of an edge. Okay, here it is introduced because they use it in a proof, but we do not do that proof. But what is subdivision? It's the substitution of an edge by a path, okay? So for instance, this is a subdivision, substituting this edge with this path. You could put also many more vertices, but all of degree 2 inside, so to say, that initial edge, okay? And it can be seen that the class of blocks with at least three vertices is closed under the operation of subdivision, meaning if you take a block and subdivide some edges of the block, it remains the same set of vertices in the block, okay? And the proof is that fact. We are not interested in that, but the corollary is this: if G is a block with at least three vertices, then any two edges of G lie on a common cycle. So understanding blocks, understanding cycles, understanding two connectivity are all things which are related to each other through these propositions. I do not want you to think about that anymore. Apart from the fact that you have applications like the one I mentioned at the very beginning of this chapter, construction of a reliable communication networks means be careful not to have cut vertices, okay? Italy has not really a cut vertex, but almost, which is exactly Bologna, okay? Bologna station joins quite most part of northern Italy to the most part of central and southern Italy, okay? And that's the reason why it was extremely heavily bombed during World War II, okay? And because actually if you stop Bologna, it's a terrible thing for all Italy, because you have other lines which are very weak, so to say. So it's not exactly a cut vertex, but in a sense it is. So we can also see something. We are thinking of every vertex equal to any other vertex, but you must have in reality also some other parameters. How big, how much, how many trains can go through that station? Okay, how many lines do come to that station? So that's why even if it is not a cut vertex, it's the deletion of Bologna as a vertex would be extremely more dangerous than, say, Ancona or La Spezia, which are alternative routes from north to south. Okay, let's go to this nice chapter. This chapter has applications, you'll find them, maybe I'll have, I don't know, because I'm going very, very slowly, but I would like to give you also some marginal talks about various applications. But please believe me, there are applications of these two concepts, Euler tours and Hamilton cycles, but they both came from a playground, so to say, in the sense that Euler tours came from a problem they were debating in the pubs of a town, Königsberg. Okay? And Hamilton cycles, which is the tougher part of this chapter, came out of a game that a friend of Hamilton, who was a very big, very great mathematician, maybe you have found Hamilton in mechanics, okay? This friend of him asked him to invent a game to sell. The game was a flop, didn't sell much, it was too easy, and so it was a flop. But it gave rise to a whole branch of graph theory. So let's see for first Euler tours. Definition: a trail that traverses every edge of G is called an Euler trail. Okay? And we are interested in a tour, which is a closed walk that traverses each edge of G at least one. Okay? And an Euler tour is a tour which traverses each edge exactly once. Okay? So a closed Euler trail. And a graph is said to be Eulerian if it contains at least an Euler tour. The thing started in 1736 because there was this fact that Königsberg is a town, a city still existing now with the name of Kaliningrad. At that time it was, I don't know in which nation. Central Europe is a very big problem because it's extremely mixed. You find in the same town 3 different nationalities of population, different languages, and so on. And not only in central. If you go to Trieste, we find many Slovenian-speaking people. And it was at that time a Polish, Russian, and German town with the name of Königsberg, and actually the mayor was a German, and there was this thing. At that time, they had only these bridges between one bank, the other bank, and these 2 islands on which the town was built. And the problem in the pubs, good for them to have in the pubs this thing, okay? The problem was, can you have a tour, which we now call an Euler tour, can you go from one place through all bridges exactly once and come back to that place, okay? And they did not, they tried, this is very nice because they tried, they didn't succeed. But they were aware of the fact that not succeeding means that it's impossible. okay? If you succeed, you see that it's possible. If you don't succeed, it's maybe because you are dumb and there comes a genius who finds a solution, but you don't know. You would like to prove whether it is actually impossible. Okay, so the mayor wrote to Leonhard Euler, a Swiss mathematician, and it's one of my gods in mathematics because I like what he did, because he did quite a lot of things with a lot of children and in great part of his life being completely blind, so a hero of mathematics. At the beginning, he was, said, I'm sorry, but I don't know what a mathematician could do about that. It's not mathematics. Ask no, ask somebody else. But then the thing was, as I said, okay, be careful because the problems in graph theory eat your brains, okay? And this problem ate his brain, and he actually invented graph theory for that, okay? So to say, because he went out after a while, he said, no, the problem is mathematical in a sense, and the solution is this. It is not possible. Why? Because he gave this theorem. We say it now in modern terms. He didn't say graph because the term graph did not exist. But an empty connected graph is Eulerian, so there is at least an Euler tour in it, if and only if it has no vertices of odd degree. Again, you have that, look at the length, it's not extremely long, but still it's not trivial, this proof. And on one side, it's very easy. Of course, if an Euler tour exists, then you have that all vertices are of even degree, because if you have entered a vertex, you have also exited that vertex. And so necessarily, you have as many edges to enter a vertex as you have for exiting, getting out of the vertex. So if you have an Euler tour, necessarily all vertices have even degree. The more difficult part is to say if you have even degrees, then it's possible to find an Euler tour. Okay, but I don't give the proof. If you want, you can look. It's not terrible, okay? There is also the notion of trail, an Euler trail, as I said at the beginning, okay? Going from one place to another place, going through every edge exactly once, okay? And when does an Euler trail exist? If and only if it has at most two vertices of odd degree, okay? If it has no vertices of odd degree, then you have an Euler trail that starts and ends in the same vertex. If you have two, you know that you cannot have one of odd degree, okay? But if you have two, you can have an Euler trail starting from one and ending at the other. Again, no proof. Exercises. Which of the following figures can be drawn? This is something I was given when I was a child, okay? Without lifting one's pen from the paper or covering a line more than once, okay? And actually, so what's the problem? Can you, is there here an Euler trail? Let's see what we can say about, for instance, the degrees of the vertices here. These here all have degree 2. Here we have degree 1, and here 4, 4, 4, 4, 4, 4. So yes, there is an Euler trail starting from here and ending here. Finding it is a different matter, okay? We need an algorithm for doing that. But the existence is assured by this theorem. This has exactly two vertices of odd degree, so we know that there exists an Euler trail from this to this because these are the only ones with odd degrees. Here,
Professor,
yeah,
when we have the odd degrees, it means that there are the start and the end of this Euler tour, right?
not tour, trail, because
Trail.
a
Sorry,
tour,
sorry,
a
sorry.
tour
I mean
ends
the
where.
Euler trail. Yes,
Sure,
yes.
sure. Necessarily, they are the origin and terminus of the trail. Okay, but how to do that? Here, it's not that trivial. You can try, okay, but I think I would bet that the first one or two trials do not work. You must be careful or use an algorithm. I'll give, not today, I don't have time today, but at the end of this chapter, there is an algorithm, Fleury's algorithm, for finding an Euler tour where one exists. Let's look at this example. What do we have here? Degree 1, degree 3, 4, 4, 4, but 3 and 3. So here we do not have an Euler, even an Euler trail. But if we delete this I would use a Fleury's algorithm on this, but modified without this sort of a tail here. If we take out this, then we have an Euler trail, okay? And here, look for yourself whether it's possible or not possible to have an Euler trail or an Euler tour here, okay? And now a problem which turns out to be not so easy. You must have imagination. So, 412. If possible, draw a Eulerian graph G with ni even and epsilon odd. Otherwise, explain why there is no such graph. So here they do not tell you whether such a graph exists or not. And so you can do what I used to do with a friend of mine for some years when we wanted to, we did not know what the answer to a big problem, still unsolved problem in mathematics was. And so one day I was trying to prove and he was trying to find the counterexample. And the day after we switched roles. I was trying to find the counterexample, and he would try to prove. Okay, and so okay, try. Can you find a Eulerian graph with an even number of vertices but an odd number of edges? And if it's not possible, explain why it's not possible. Okay, prove that it's not possible. Hamilton cycles. Okay, I don't know whether Hamilton, who came several years after Euler, was inspired by what was already known of the work of Euler on his problem. Okay, and so when his friend Graves asked him for a game to sell, he invented this game. It was too easy. This is the schema of the edges of a particular polyhedron, which is called dodecahedron. Okay, and the idea was to go from one vertex, coming back to the same vertex by touching every vertex exactly once. Okay, and actually it was too easy, and so it was not solved. Okay, I think he got I think 150 pounds at that time. It was not too little, but okay, he didn't become rich because of this. Okay, and so it is very, very similar to the idea of the problem of Euler, okay? Eulerian, go through every edge exactly once and come back to the initial point. Hamilton, go through each vertex exactly once and come back to the original point, okay? Looks similar, very similar. Absolutely not. On one side, Eulerian the problem completely solved, and you have seen what it is. You have a Eulerian tour if and only if all vertices are even. End of the game. The theory ended as it started, okay? When Euler took the problem in his hands, well, it was already at the end. You just had to invent the algorithm, but whether or not such a tour exists was already solved from the beginning. Hamilton starts in this year, and now we still do not know which graphs are Hamiltonian. Meaning what? Meaning that a Hamilton cycle exists in that graph. We do not have a characterization. I already spoke about characterizations in mathematics. You have something of interest for you, but you don't see how to solve it. You have something apparently of no interest, but which is a necessary and a sufficient condition for that. Are you interested in the fact that the degrees of a graph are even or odd? Maybe not. In the pubs of Königsberg, they were absolutely not interested in that. They were interested in the problem. Is there such a tour or not? So, problem. Is there such a tour? Eulerian, if such a tour exists. This is what interests me. But I cannot see immediately whether such a tour exists or not. Even degrees. This is something I can do. I visit each vertex and count. When I'm done, even if it is with 1,000 vertices, if I found that all degrees are even, I know that in that graph an Euler tour exists. You see a very good characterization. This is a prototype of characterization in mathematics, okay? No, we do not have such a thing for Hamiltonian graphs. So we have, and I'll show you. No, I can show you one now. Some necessary conditions, some sufficient condition. We have also one necessary and sufficient, but which just displaces the problem and does not solve it. Okay. For instance, we have this. Simple but useful necessary condition. If G is Hamiltonian, then for every non-empty proper subset of V, S of V, the number of components of G in which you have deleted the vertices of S is less than or equal to the number of vertices of S itself. So it's something rather heavy to see, because you should take all proper subsets, count the number of vertices, see what happens if you delete those vertices, and what happens is, if it is Hamiltonian, then you have this inequality. But if you have this inequality, you do not have any guarantee that the graph is Hamiltonian. Be careful again not to invert an implication. What you can use is what I have already recommended to you, the counter positive. So what happens is that if you find even only one subset S, such that if you delete the vertices of S, you obtain more components than the number of vertices of S, then you are sure that your graph is non-Hamiltonian. Okay? There are also other ways of seeing that a graph is non-Hamiltonian. Take this, the Herschel graph. How can how do the authors show you that this is not Hamiltonian? Okay, why? It is bipartite, and you can check this. Why? Because it has. We know how to check whether a graph is bipartite without finding the bipartition. Do you remember another wonderful, very simple characterization? It is bipartite if and only if all cycles are even. Here we only have even cycles. You do not find a not cycle. So you're sure that here a bipartition exists. Okay? Okay, so it means that if you have a path, and if you have a closed trail, starting on one vertex and coming back to that vertex, then you go from one to the other, from one to the other, to one to the other set of the bipartition, okay? But since this graph, still being bipartite, has an odd number of vertices, then it's not possible that you come back to the original vertex by a path which touches all the vertices exactly once. Okay, if it is a path, if it is a cycle, it goes through each vertex, apart from the first and last, which are equal, exactly once, but touching all of them. Okay, why? Because the first will be in X, the second in Y, the third in X, the fourth in Y, and so on and so forth. Okay, since they are odd, either you miss at least one or you repeat at least one. So it's easy in this case to say, no, this is not Hamiltonian. Don't try, because there will never be a Hamiltonian cycle in this graph. Maybe there is a Hamiltonian path starting on one vertex and ending in another vertex. You can try to find a Hamiltonian path if there is one, okay? And you have this, but this is rather heavy to use, and we have also others which we'll go through tomorrow. So, see you tomorrow. Ciao.
Thank you.